Welcome to part 1, information structure. We will introduce the basic concept using a thought experiment. And thought experiment is about coin tossing. In one closed room, Nicole has a nickel. In another closed room, Dimas has a dime. So the sample space here contains all the possible outcomes of this experiment, which in this particular case is very simple. It's only 4 possible outcomes that we will call omega 1, omega 2, omega 3, and omega 4. I'm going to illustrate this using my iPad. So we have the 2 rooms, Nicole in one room, Dimas in the other room. And Nicole here has a coin, which is a nickel. And Dimas has a coin here, which is a dime. So they're going to do their experiments. The question that we want to address right now is the following. So I've repeated what omega is. How does Nicole describe the information that she can see about this experiment? And in order to do this, we realize that Nicole can only just see the nickel. So if the nickel comes out heads, she cannot actually discern whether it was omega 1 or omega 2 that occurred, because she doesn't know what is the result of the dime. By the same token, she knows if the nickel comes out tails because she can see it. But then there are 2 elements in omega where the nickel comes in tails. So to visualize this, what happens is the following. If we picture the set omega as having its 4 elements, it's a very simple example, but it contains the elements for much more complex models in probability. So if we think about omega this way, what we see is that Nicole actually creates a partition of omega into 2 subsets. The subset corresponding to heads on the nickel, and the subset corresponding to the event that the nickel comes out in tails. So what happens is that the way that she sees the experiment, this introduces a partition of omega. And this partition basically describes mathematically the way that the situation that we have, that Nicole is only just looking at the partial information. Before we go on, we're going to introduce a third character in here. So our third character here is Liz. And this character first of all, this character is sitting outside. Now, we assume that there are video cameras on the ceiling that can actually recognize what was the outcome of each of the coins. So these are going to be connected, these 2 cameras are going to be connected to something similar to a traffic light. So what we're going to have here is the light will turn green when we have 2 heads. So both the coins are showing heads. The light will be red if the 2 coins are showing tails. And otherwise, the light will be green. Now Luz is sitting comfortably and she cannot actually see the rooms. And Nicole cannot see Dimas or Luz. Dimas cannot see Nicole or Luz, and Luz cannot see Nicole or Dimas. So again, Luz has yet a third perspective, which is a different perspective from Nicole and Dimas. So each one of the 3, each of the observers has a different information structure about the experiment, which in computer science we would call the ground truth. So we're going to go back to the slides now. And this is the exercise for you. Describe now the partitions of omega as they are viewed by Dimas and Luz. So now you have 3 players. We've done Nicole together, and now we're going to do Dimas and Luz. An element of omega is called an outcome, but a subset is called an event. A collection of subsets is called a sigma algebra when it satisfies these 3 conditions. The first condition tells us that the empty set has to be in the collection. The second condition is a condition which is logical. We are building a model, a mathematical model for random phenomena, because we want to be able to assign likelihoods or probabilities to events. So if you have a model where you want to talk about the probability of rain tomorrow, for example, you have to be able to talk about probability of no rain tomorrow. And so this is expressed in this way. If an event is contained in the information structure, then the complement of the event is also contained. And we annotate that by putting a superscript C on the symbol of the set. So this is what happens. And the third condition is, again, a logical condition. When we have events, then we want to be able to talk about event 1 and event 2. And when we talk about that, that is the same as the union of the sets. So we require that the information structure, that a sigma algebra, contains the union of the events that it contains. And we call a space omega with a sigma algebra a measurable space. We're going to be talking about that in the sequel. Let's go back to the example 1 to form the sigma algebras. Nicole, Dimas, and Luz have partial information about the experiment, and for each one, we can define an appropriate sigma algebra that models this situation. I'm going to do it with Nicole, and I will leave as an exercise for you to do the same thing for Dimas and Luz perspectives. From the perspective of Nicole, the heads in the nickel appears in both outcomes, omega 1 and omega 2, as we have seen. So she cannot really distinguish between these two. And similarly, the tails appear in omega 3 and omega 4. So in order to form a sigma algebra, we go onto the properties. We know that the empty set has to be there. So there it is, the empty set. We know that the complement of every set has to be there. And so the complement of the empty set will in this case be omega. So omega is also contained in there. And then we have the event of heads for the nickel and the event for the corresponding to tails for the nickel. And then if we create all the unions between these events, that's what we get. This is a relatively simple sigma algebra because it basically just is built with 2 events. Another way to construct it, which is particularly useful for computer scientists, is to create the power set of the partition described by Nicole. And that will give you the sigma algebra, it's just the power set. So as an exercise, please build the sigma algebras for Dimas and for Luz. And again, I suggest you take a pause in the video and that you do the exercise before going on. Given a measurable space, a collection of sigma algebras on omega is called a filtration if it is a collection of
non-decreasing sigma algebras. So what we have here is that all of the events that are contained in the sigma algebra ft are also going to be contained in the sigma algebra t plus 1. So in terms of information, all the information that we have in the past is going to be appearing again in the future. So that's why the concept of time labeled by T is captured by the concept of a filtration. The events that are observable in the past are also included for the future descriptions. And because there is increasing level of detail in a filtration, then as time goes on, the past information is not going to be lost. As an exercise, consider now the 3 sigma algebras that you have already built from example 1. We have for Nicole Fn, for Dimas Fd, and for Luz we have Fl. Call F with no subscript the power set of omega, so it contains all of the subsets of omega. Explain which of these fields are contained in other fields, and do you see a sigma algebra? This is the second example. It's called the game of craps. And this example, the game of craps, is very well known in casinos and also in probability books. There are 2 dice, and so when you throw the 2 dice, the outcomes can be any number between 2 and 12. So that's going to be basically what I call omega. The sample space is any outcome between 2 and 12. Now, there is a subset that will be very important. I'm going to call it C, and this subset is the numbers 4, 5, 6, 8, 9, and 10. And the game works as follows. In the initial step, if the initial outcome is a 2, a 3, or a 12, you lose the game. If the initial outcome is a 7 or 11, then you win the game. But if the initial outcome is in the set C, then you continue playing. And that's why I called it C, because it's the continuing set. So what happens when you continue? Well, if the initial outcome was X, which is any of these numbers in the set C, then the game continues as follows. If you throw a 7, you lose. If you throw again the initial number that you had thrown, you win the game. And else, you continue playing. So now we're going to have a little view of the game of craps. I'm going to show you my iPad again, and we're going to see how can we describe this game in terms of the information structure that it has. Well, it is complicated because we might ask ourselves to begin with, what is omega here? It's not as simple as with the first example where we had only 4 possible outcomes. This game, in principle, can continue up to infinity. There's no bound on the number of steps or stages in the game. So let's visualize it as follows. If the first outcome is between 2, so I'm going to put here, the time t. So for t equals 0. If the first outcome is 2, 3, or 12, then we lose the game. If it is 7 or an 11, then we win the game. And if it's any other number x, which is in the continuing set, then we continue. Meaning, so we got an x here, meaning we continue and we go up to time equals 1. So this will be, the initial one is done, and now we continue. What happens when we continue? Well, if we throw, again, the same number as we did at the first time, then we win. If we throw a 7, then we lose. And if we throw anything else here, then we continue. If we continue the game, then we go to t equals 2. And again, if we throw the initial number x that we had at the beginning, we win. If we throw a 7,
we lose, and otherwise we continue, and dot, 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 the game goes on like that. So that's the way that the game plays. So how can we visualize this? So a way that I visualize this is as follows. If this is a set omega that I cannot really describe in words easily because it is complicated, but I do know that on my initial step, so initially t equals 0, this set is partitioned into 3. There's this set, the losing set, the winning set, and the continuing set. So if I can visualize this, I'm going to say that in the first stage, the information that I have divides the space into 3 parts. There is the losing part, there's the winning part, and there's the continuing part. Now, on stage number 2, so this would be my partition P1, or P0, sorry, because we start with 0. Now, what happens at time T1? Once we have T1, we can add more information. So the continuing set here is going to be divided into 3 other subsets. So it's going to be partitioned, again, into 3 areas. One area will be winning, the other area will be losing, and the other area will be continuing for set number 2. So this will be the partition P1 that contains the previous one, plus it has more detail on the continuing set. When we go to, if we are in the continuing set and we go to stage 3, then we're here. Again, this divides the space into 3 parts. A winning part, a losing part, and a continuing part. And that will be P2. And so as the game goes on, we gather more and more information. So as the game continues, there is more detailed information. And this is, of course, the concept of filtration. If we take this sequence of partitions and we think about the power set of these partitions, that's going to give us sigma algebras. And the collection of these sigma algebras is going to define a filtration. This finishes the lecture for today, and next we're going to go into part 2, random variables and random processes. So I hope to see you soon. I'm going to stop the share, and then I'll see you for next time.